All right, good afternoon, everybody, and welcome to our first KML Symposium. My name is Clemens Heitzinger, and together with Stefan Woltran, I will guide you through today's program. In a few minutes, we will start with the colloquium talk by Pedro Cabala. He will talk about knowledge-based AI as a mold of human reasoning. There will be a coffee break afterwards, and if you're joining us here live, you will also be able to enjoy the beautiful view over Vienna. Most importantly, we look forward to discussions about AI, ML, and our newly founded center. At 4 p.m., we will continue with the colloquium talk by Mohammad Ghavamzadeh. He will join us live from California, and he will talk about handling constraint in Stochastic Bandits. At 5:30 p.m., after the second coffee break, we will continue with a public lecture by Edward A. Lee on the limits of machines and the limits of humans. Afterwards, there will be a reception, and again, we look forward to meeting you there. Now over to you, Stefan.
So welcome everybody, also from my side. It is my great pleasure and honor of today, Pedro Cabala. So he's an associate professor at the Computer Science and Information Technology Department at the University of Coruña in Spain, Galicia. And when he's from the symbolic AI camp, he's working on the foundations of answer set programming and logic programming, and with a special emphasis on temporal, causal, epistemic, and qualitative spatial reasoning concepts. And I remember we met first 20 years ago, I think, at FLOC in Copenhagen. So FLOC is a huge conference in the logic and symbolic AI community, which is also taking place this summer. But let me also mention that we have another big AI conference this summer here in Vienna, the ICHCAI conference in July. Yes, so it is great to have you now here in Vienna as a guest professor. So you visit us for around 3 months this time. And yeah, maybe just a few words. I mean, you have been very active in our research community. Of course, Pedro is currently a work group leader of an European cost action called DIC for ASB, which means which is on automated reasoning applied to digital forensics. But I think today you will give us a more broad overview about the work you have done and the domains you have investigated, and I'm very curious and looking forward to your talk. Thanks for being here, Pedro.
How do you do the, because I don't know, full screen, yes? Because the text is in German, right?
Yeah.
Kind of hard.
I try Control L, it's my first try usually, not good. You'd already tried this. That one?
Okay, thank you. Well, actually, I have to start apologizing because I wasn't sure about the orientation of the talk I should give or the public I would meet. So probably many of the things I'm going to tell are just trivial for you, or maybe for other people are not, I don't know. And also, I will divide the presentation in 2 parts. One part is about, let's say, the motivation of what I do. And the other part, a bit more on detail of what I do. But the talk is more focused on the first part, actually. So I don't know how it will go, right, let's say. So the first thing is, what is artificial intelligence? I guess everybody starts with this, right? And the origin is the Turing test. Nowadays, the Turing test would be very easy to make, and in fact, it is being done it was done in a competition, that you could use a chat, right? It's very easy. You don't need all the paraphernalia that Turing invented to make the test. You have your phone and you want to know whether you are actually talking to a person or you rather are talking to a computer that is generating the chat. Of course, there are new things like emoticons and things like that that should be used in order to cheat you and make you think that you are treating with a human, right? But of course, the Turing test has two clear problems that have been spotted a long time ago. And the first problem is that what happens if I ask you a precise answer to a given question, right? Which is the square root of this number. Do we expect that the computer is accurate and give us an answer, revealing itself not as a human? And I would say yes, because I'm interested in a precise computer, not a computer making an imitation. And the other problem has to do with feelings, right? If I tell the computer, delete all our conversations now, I don't expect he asks me whether I am angry with him. I expect to delete everything quickly, maybe because there is some important reason, right? So rather than general or let's say imitation artificial intelligence, I'm more focused on what we could call rational artificial intelligence. And in the definition that John McCarthy gave when he coined the term, is the science and engineering of making intelligent machines, especially intelligent computer programs. So as you can see, he's saying that we look for a way of an intelligent interaction with the computer that is more practically oriented, right? So how is this interaction? So the tools in artificial intelligence, after all, are tools. And when we build tools, these tools may produce new human skills. Think about the typewriter, right? We design a tool and then we acquire the capability of typing. And in fact, we have to learn to use it. Or think about a car, right? The car is not trivial to be driven. We have to learn how to drive. And sometimes the decisions we make in the tool are quite arbitrary. I don't know if you know this false legend about the design of the QWERTY keyboard. Apparently it's not based on a real story, but it could be the case that it was designed in a particular way for a physical typewriter. And now we have inherited, whatever was the reason, we have inherited that design in our phones. And by the way, I have to learn the QWERTY Z in German keyboards. I was not aware that this was a difference at all, right? So the tool we design also makes us to think about things as natural where they are not natural at all, right? And the same happens when you try to move into closer to human. Right? Think about voice assistants where you can talk to them, but after a while you discover that you cannot talk about everything to a voice assistant, right? And you have to choose very well what to say and in the words you have to choose. The same happens when you make a search in Google, right? You soon discover that it's better to put a bunch of words rather than a structured sentence, especially if the words you think are going to be statistically relevant. So we humans, first we designed the tool to be nice for the humans, but then we humans learn how to use the tool and exploit its utility. So what do we expect for intelligent machines? The first possibility is to attach to current human languages, interfaces or tools. As an example is thinking about the autonomous vehicle as it has to be a car that has to be driven exactly like humans drive, that has to recognize human traffic lights, human signs, and human codes, right? So all the effort in the autonomous vehicle is pushing in the direction of we want something that works essentially as humans would use. The other choice is exploit the current technology with a reasonable adaptation. I expect that the human will adapt to the technology as well, a bit at least, right? And think about the train. So we had the vapor machine, right? It was not easy to move with it. We invented the railroad. Huh? And nowadays trains are autonomous, much more autonomous than cars. And it's a reasonable balance between what we have in the technology and what we can expect from the humans. Also, it happens with ships and planes. No? Most of the time, they are actually autonomous. So maybe there's a lot of effort here that shouldn't go in that direction. Think about how big stores for companies, it's not in the slide, but this is a store in Amazon, right? How they work. They have autonomous vehicles. Well, actually, they are not so autonomous because they have a central plan for moving, but they move around, and they have the rails painted in the floor, right? So why should we make all of an effort of moving around anywhere if we can paint the rails in the floor? That is also, again, a reasonable balance between what you can get from the technology and what you can do. So if we talk to the computer, we can think about it like an alien, right? Imagine that we have an alien there, we want to talk to it. It is like an alien because the way in which the computer reasons is quite different from humans, right? How do we talk to it? I don't know if you saw this movie, The Arrival. It poses a similar problem to what I am proposing here. Actually, it's based on a thesis in linguistics that is called the Shapiro-Whorf thesis that says that language shapes thinking. So the way in which you speak actually shapes the kind of reasonings you make. And this is completely nowadays rejected in linguistics, at least for human thinking. But I claim that with the computers is a bit like that. Because the way in which you talk to the computer makes you understand it as a kind of different tool. And think about how the computers were used in the beginning. Essentially, a computer in the beginning was a function where you gave the input and you got the output after a while. So you had to wait some time and you have to physically build the input, right? And the input was the big invention of the computer was that the input had the data and the program together. So we had these tape computers where you have to prepare the tape, feed the tape to the computer, function applied, and then you get the output. Then we had time sharing, and suddenly the same computer was a bit like several computers working magically at a time. So you could feed several programs, and the computer decided sharing some time of computation among them. So again, now we see the computer as something that can handle multiple tasks at the same time, right? But in all the cases here, we have a function that is applied to the input and get the output. The programs we write are expected to terminate, for instance. It wouldn't be very bad. It would be very bad if the program doesn't terminate. And most of the effort had to do with termination of the algorithm. But now think what happens when reactive systems come into play. Your email server, for instance, is not expected to terminate. The other way around, it should be running all the time. You want to receive the email continuously, right? So reactive systems are a different view of a computer, quite different from the very beginning, where you have an environment that is providing you information that you can sense, let's say, and then you can send information to the environment, you could act. And the environment, of course, can have other computers connected as well, acting in the same way. So in this, under this understanding, the computer should not terminate. If it terminates or if it gets a deadlock, there is a problem. So you can see that the ways in which we use the computer change our perception of the machine. What happens with machine learning systems today? They are data driven. So this is how we see it. We have a huge amount of data. We have big data, lots of sources. Sorry for the drawings, are quite childish, right? You feed them to the computer provides an output. Normally, it's a classification or a prediction, right? Normally something like that. And also we have this loop. We can make the computer to feed itself, right? Play a lot of Go games to learn something else, right? Under this view, we don't have the program anymore. I don't know if you realize it. We don't feed the program. The program is the learning algorithm. So the way to talk to the computer is providing data. That is the way we can interact with it. We cannot say anything to the computer anymore, right? And this is a quite distorted view. To solve any problem, the first thing is start looking for the data. And then we see it every day. I don't know if you know other people that are always worried about where is the data set, right? And of course, I'm not saying that this doesn't make sense, but it makes sense if applied to the proper problem. Imagine that you are in the 50s and you don't know yet how to sort a list, right? But we have this technology in the 50s. So the only thing we can do with the computer is feed in data. What would you do? Well, provide a lot of lists that are already sorted, provide a lot of lists that are not sorted, maybe very long lists, maybe millions of lists, feed them to the computer, and you apply some machine learning algorithm that would tell you, given this element, I predict that the position in the list is 22. And of course, you can get very nice results. For instance, imagine that you get 90.99% of accuracy. Would you be happy with that? Because we are saying that 1 in each 10,000 cases you try to sort the list is not well sorted. Well, this is the situation nowadays. So for some problems, we are doing this, and we have to be a bit careful with that, because of course, all the effort with the sorting algorithms wouldn't make any value, added value, right? With the quicksort algorithm, proving the correctness was a hard problem, right? Imagine the quicksort algorithm in the beginning was not in a recursive way. It was handled with several stacks. Improving the correctness there was a hard thing. In fact, I guess that probably part of the effort by Hoare in formal verification was due to that. I have an algorithm. I want to convince you that it is correct. And look at the word there. The key point is not accuracy. For some problems, the key point is correctness. And when correctness is in place, you have to adopt a different methodology, right? So in artificial intelligence, there is a whole area that is knowledge representation, and that can be summarized in this sentence by John McCarthy. I like it a lot. In order for a program to be capable of learning something, it must first be capable of being told it. So you expect that the program learns something, but doesn't understand when you tell it directly. So in order to have learned something, in order to have acquired some knowledge, you have to be able to represent that knowledge at least, right? So to communicate knowledge to the computer, we need an explicit representation. And let me put another example. Imagine that you train an autonomous car to drive here in Austria. And of course, you play all the experiments like the Google car or whatever, all around in all the streets. And now you move this car into the UK, where you have to drive on the left. What happens with human intelligence? Of course, when we learn how to drive, I'm not saying that we reason all the time, right? We have to learn how to react, how to brake. And this is something that is more similar to machine learning from data. But when we go to the UK, I don't know if any of you have had this nice experience, you discover that the driver license is perfectly valid, which is kind of surprising, by the way, shouldn't be. And they say you, okay, anything you did on your right, you have to do it on your left. And that's all. And I'm not saying that you are as good a driver as in your original place, but you do it reasonably well. And after some weeks, you end up driving in the UK as well, right? So it's a combination of learning, but also reasoning that is having place here. And you got the message, right? Drive on the left. It's just a sentence. There is an explicit representation of what you have to do, which is the machine learning approach. You have to train your car in British roads. So it's, again, data-driven, right? So what McCarthy proposes is, in order to tell something to the computer, we have to use logic. And here is an innovative thing that is using logic for common sense reasoning, which is kind of a dirty thing, right? Because logic was in a different dimension. using logic for talking about going to the airport was kind of, I don't know, not too elegant, let's say. But it is an important idea, I think. Which are the desirable properties of good KR formalism? And this is my list, but please, if any of you want to add something, go ahead. I would say simplicity. This means that you don't have too many constructs, and the constructs you have are simple. You don't have to build difficult expressions, right? Like, for instance, if you think about using nested functions with thousands of parentheses, that is not simple, right? I would also say succinctness. This is related to simplicity, but it's not the same. Succinctness is that you can tell things with short, compact descriptions. Maybe you use very complicated constructs, but the description is really short, right? Let me put an example. If you think about SQL, is simple, but you have to use a lot of words, right? Maybe you use data log. It's much more compact, but you have to read it twice, right? Because you have to be careful how to use the variables and the bodies of the rules. It has to have a natural understanding. It doesn't matter that you have the other two things, but there is no mapping with human language, because then you lose an important part of the goals you had here. Is humans communicating knowledge to the computer communicating knowledge to humans. If there is no correspondence with natural language, it's quite an effort to find out what you are reading, right? It has to have a clear semantics. And well, you could disagree here, right? I would be happy using natural language, for instance, but natural language can get you in an important mess if you deal with ambiguous sentence, right? Imagine controlling something really serious where you can, okay, what do you mean when you say something? And there are actually several interpretations. So ambiguity is not nice when you treat with a guy, with this alien that is very strict, right? And it has to have an efficiently computable automated reasoning method. Otherwise, all the effort, you can have 1 to 4. But if it is not computable, then you cannot use the computer for this language, right? This is clear. Or if there is not efficiently computable method, at least you have to know it. At least you have to know which is the complexity of the task you are requiring. Probably I'm talking to the wrong audience here. I didn't know whether I would have general public or not, but I guess that we are all convinced here about this, right? And one important property that was proposed by John McCarthy is elaboration tolerance. This means that the small changes in the problem you try to solve should mean small changes in your representation. You don't have to rewrite the whole representation from the beginning just because there was a small change. Let me put an example. This is the classical 8 puzzle problem where you have these little pieces you can slide. It is a typical example in any AI course, but it's an example for search algorithms. Normally it's used for search algorithms, right? So imagine that you have a solver, I don't know, you built an A* program, a search program with heuristics and so on, very fast for solving the 8 puzzle problem or the 15 puzzle problem or whatever. But you have said that now, rather than having 1 hole, you have 2 holes. Actually, it wouldn't be the 8 puzzle, it would be the 7 puzzle, right? What does this mean on your tool, right? This is the key thing, because it's a small variation of the problem, but maybe your whole algorithm has to be rewritten from the beginning because you chose the wrong representation. Like my state is a pair of positions, the column and the row where the whole is. And the heuristics is built on that. So this is a critical feature, elaboration tolerance, because it may be the case that you chose the wrong way of using your language, but there is a way in which you can adapt this change. Or it may be the case that your language regardless the effort you make, cannot incorporate this small variation. And that would be a problem from the knowledge representation point of view, right? So suppose that we use automata as knowledge representation. It has a clear semantics. Diagrams are very easy to understand for humans. If you see a diagram, you see very quickly, for instance, whether there is a path between a state and another one. You see it immediately, right? You just paint the automaton in the wall and you can check it very quickly. It has very well-known computation methods, but what happens with elaboration tolerance, for instance? Imagine that you build the automaton, would be quite an effort because the 8 puzzle has more than 100,000 states. But imagine that you could draw an automaton in the wall and that you change the state, the number of states, the transitions among them have to be rethought completely from scratch. Practically, there is no systematic way where you can rebuild the automaton from the other one. You have to start from zero, right? What about if we choose natural language? Well, natural language, of course, would be very nice if we could talk to the computer using natural language. But I claim that it has to be an interface to someone else, to something else. Natural language, of course, has a natural correspondence to natural language because it is the same object, right? And it is extremely flexible. I don't know anything more flexible than that. Maybe you can tell me, but look about the other example. We have now 2 holes. It's just 5 words that change the picture completely. There is a paper by John McCarthy that is, I think, 20 elaborations of the missionaries and cannibals problem, where he puts all kind of possible minor changes in the problem. Some of them are quite tricky, like, I don't know if you know this passage. You have the missionaries in one side, the cannibals. No, the missionaries and the cannibals in one side. You have to move them. One of the variations is that the probability that the missionaries eat the cannibals is 20%. So imagine that you had all your logical representation and suddenly you have to incorporate probabilities there. Right? It's like killing you, no? So natural language is really, really flexible. It's too flexible, to tell the truth, because it's not simple. Look, the problems I had with German. So the only people that can learn natural language are children, which are much more smarter than us. And for an adult, learning a new language is not simple at all. And it's too ambiguous, right? There are lots of examples, and the natural language community know about them. There are plenty of examples where you have to remove the ambiguity, for instance, by doing context reasoning, and it's not trivial either, even if you use the context to interpret the sentences. But moreover, what about computability and complexity? In natural language, you can express anything. You can express undecidable problems. You can tell the computer using natural language, do something that we know that is undecidable. You can tell a computer a paradox, right? How solve a problem that has no solution. How do you deal with that, right? So it's too much, right? A limited version of the natural language may possibly make more sense. So logics are a reasonable choice. They are simple, they have correspondence with language, they have a clear semantics, computation methods, complexity assessment. Perhaps the problems we face in the beginning of knowledge-based AI is that at least classical logic had some problems with elaboration tolerance that led to famous problems like the frame, ramification, qualification problem. And the solution to that, as we will see later, is using the fold reasoning, being able to draw conclusions in the absence of information. So the next part of the talk is about how this has affected to logic. If we think about logic, probably I'm not in the right place to make this review of the story of logic, right? But we have like 3 ages, the philosophical logic that started with Aristotle. By the way, this statue is here in Vienna. It's in the History of Art Museum that I recommend to visit. And from Aristotle, it passed to the Islamic culture like Avicenna, and then back to Europe into the Middle Ages with St. Thomas Aquinas. Of course, there are many more names, but essentially we have this big, large era of philosophical logic. After that, we jumped into mathematical logic with the birth of classical logic, propositional logic, and predicate calculus. By the way, the notation of predicate calculus was actually more due to Peano and Gensen, because the original, I don't know if you saw the original notation by Frege, but it's scary. You cannot practically read anything. But why do I say this? Because nowadays we see the for all symbol at the exist symbol, and everybody would say, this is natural. Well, no, this is something we learn and we adapted to it. And also the disjunction and the conjunction has a history behind, right? And then David Hilbert with the proposal of using logic for building a building for mathematics, right? So the worry at this point was that logic were able enough not only to talk about truth, which was the philosophical understanding, but also to set the basis for all the mathematics. And this, the famous Principia Mathematica work was about that. Of course, it was then we had the crisis with the incompleteness theorem, and Kurt Gödel is there in red because it's possibly one of the most important, or perhaps the most important logician. And it was here in Vienna. It's kind of a responsibility, you know, to do logic here in Vienna, having this guy around, or having had this guy around. But also Alfred Tuskey plays an important role because it's the idea of semantics and model-based. It's related to what I will talk about later. And then the third age came talking about things like lambda calculus, Turing machines, recursive functions. So let's talk about what a computer can do using logic, right? And the other way around. Let's see what we do with a computer is correct. So let's use logic to see what if our programs are correct. No? So we have the formal methods discipline with people like Hoare, Dijkstra, Dana Scott, or with the branch of model checking, right? Let's see if we don't find any mistake by checking all the models. By the way, 3 people in this slide were here in 2014. It was a very nice event here, and we had all these people moving around. It was kind of a impressive moment, I would say. By the way, I was just collecting the dates. I didn't know that Clark passed away a pair of years ago. So how all this story of logic affects to what we tried in artificial intelligence? Well, there are 2 other applications of logic, that is using logic for programming. That's also an important thing, logic programming. And here you have Robert Kowalski, who used logic as a semantics for logic programming, and then using logic for common sense reasoning. Well, there are things that are shocking, let's say. If you keep all this story behind, first thing is epistemic reasoning. Agents have incomplete knowledge. How is it you can have incomplete knowledge about integer numbers and play with it? I don't know. How can you express that? I don't know whether this is a prime number. No, you have to know it, right? It's part of the thing of the incompleteness theorem is that it was a shock because we were expecting that we could know everything. But an agent in nature has to handle this situation and acts intelligent by not having information. That's an important thing. And not only knowledge, but also belief. That is, an agent has a belief on something that may be not true. And he may, it or she may know that this is a belief and not knowledge. So she may agree that it could be the case that her belief is not true in reality, right? Second, you have temporal, right? So something that is believed or known today, tomorrow is to be not known or not believed. And you have to incorporate, you have to update your knowledge, you have to incorporate your beliefs. So again, think about, I don't know, any of the big names I said before, thinking that, okay, so maybe this theorem is true today, but let's see what happens tomorrow, right? Something like that. Also, default reasoning is a bit a jump farther. Because it's not only that you have incomplete knowledge, but you jump to a conclusion without that knowledge. That is rejectable from all the point of view of any logician, right? At least in the past, not today. So with more information, of course, it doesn't matter because now you have more information, you can retract what you concluded before. And also causality, I think that this is very important because causality is about answering why you got a conclusion and finding an explanation, or why not, which, by the way, are quite different questions. Why I am here, because I was invited by Stefan, right? Why I am not swimming in the ocean, well, the explanations could be quite long, but maybe the intelligent reply to that is, why should you be in the ocean? Right? Why are you expected to be in the ocean? So normally when we ask for a cause, it's because it breaks a default. Ah, no, because I was expecting you. I told you to come swimming in the ocean. Ah, you didn't come. Then the question of why not makes sense because there was a default that was broken, you see? So all these kind of things are not in the study of logic in the past and are very important. And causality is also very important for real learning. What do I mean by real learning? Learning nowadays is very good for prediction and classification, but it's not acquiring knowledge. We are not acquiring knowledge from what we learn. If we expect someday to use learning to acquire new knowledge, the computer can tell us something new. It has to deal with causality. It has to be able to say why and to explain why, right? So which logic should we use? I don't know how are we going with time. Well, you know this sentence, right? That natural numbers were created by God. Everything else is the work of man. And in logic, we have kind of the thing with classical logic, right? Classical logic is like something you got from God, and everything else is the work of man. To tell the truth, McCarthy, maybe I'm making a wrong claim, but I don't think he would like to go too far away from classical logic. You can see that he used circumscription, which is a sentence in second order logic, not any sentence, it has a particular shape, but other than that, he would not like. And he has this paper that's modality C, modal logic now. So he didn't like experimenting with different kinds of logic. But the truth is that we have an infinite number of logics. We have families of logic that you can parameterize them infinitely, as much as you want. So propositional, first order, higher order description, intuitionistic, intermediate, multi-valued. So it's quite difficult to explain anybody that you make logic with this view, right? And not only that, they can be combined, and then you kill me, right? You can take a multi-valued logic and then combine it with a model and something else. We do it all the time. So it's kind of like this sketch of Monty Python where you have a spam everywhere. You can combine with a spam as much as you want, right? So I guess that the answer is it depends on the purpose or the application. You have to choose a logic, right? And this is a difficult task because if you have too much freedom, it can be counterproductive. And here I have seen two methodologies. Maybe you can correct me. One is the top-down methodology, where you define a family of logics, many properties, and then you see what happens with them. Study these formal properties and then choose accordingly. I want to do this, then I would choose this logic because it has this property, this other property, and this other one. So this would be the top-down methodology. And the bottom-up methodology is the other way around. You start from problems you want to solve. You formalize a computable solution. Maybe you cannot use any syntax. You limit the syntax, you limit the semantics, but you solve it. And then you jump into a generalization. And normally you go standardizing things because you have the tool that does the thing. And the way in which you use the tool, you remember what I said in the past, no? Becomes the standard, right? So more or less, the first approach is normally followed by logicians or mathematicians. They think about all the possibilities. What happens if the function is non-monotonic, and what happens if you can vary this and that? And then they like to study a lot of different possibilities. Whereas clearly, simple examples is the methodology we have used in knowledge-based AI from the beginning. We start like Tweety can fly or things like that, right? Which is better, which is worse? I would say that we need both of them. Because the really nice moment is when you find that you find something and you got there using different approaches and you get the same object. For me, that is a discovery. And this is something different from an invention. You can invent many logics as much as you want. But if you reach something and somebody else was looking for something and reached the same point, it's like a discovery. You discover a new island, right, in the map. Okay. So this was the first part. I'm not sure how much time I have, but the second part of the talk is more related to what I do. And this has to do with the stable model semantics for logic programming. It was first proposed as a semantics for negation as failure in logic programming, but soon it was discovered it has a strong connection with default reasoning. As we said before, it is very important for elaboration tolerance to have a formalist that is capable of performing default reasoning. And soon they discover connections to typical approaches in default reasoning, like default logic, epistemic logic, or circumscription. In fact, there is this paper, 13 definitions of stable models. We have more than that nowadays, 12 years afterwards, right? So as I said before, these are hints that you found something, right? I'm not saying that it's the right or wrong, but it is something that is there and it's not probably an invention. Well, possibly it's not the right place to talk about answer set programming. Answer set programming is a methodology built on top of stable models, also known as answer sets, to perform model-based problem solving. It is NP complete, similar to P complete for the disjunctive case, and this result was proved by people here in Vienna. And actually, Vienna is one of probably the most important place for fundamental answer set programming, or fundamental theoretical in connection to complexity in answer set programming. We have a large list of applications thanks to efficient solvers. This is one example, for instance, that is in the Potasco group in the University of Potsdam, where you remember that the autonomous thing. Well, actually, this is being formalized and solved with answer set programming, because after all, they have made a complex problem into a discrete problem where you actually have a grid with rails, imaginary rails in the floor, right? So you can pose it as a planning problem, a multi-agent path-finding problem, and then use answer set solving for finding minimal solutions. But the list of applications is really, really large. Probably this slide is getting older and older. I have to go adding more and more things all the time. What about logic? Well, we also have a logical building for ASP. This is not the only approach, but probably I think is one important approach. And this is the one proposed by David Pearce called equilibrium logic. Equilibrium logic, I would say, is also a discovery because it connects to other logics from the tradition of logicians, right? It's a logic that is obtained as some selected models in an intermediate logic. An intermediate logic is something that is in between intuitionistic and classical. It is the logic of here and there. But moreover, this here and there logic happens to coincide with something else. That is Gödel's three-valued logic. And this was discovered afterwards. So you see that you go touching the same thing from different angles. So there is some object there that has some kind of different dimensions somehow. Right? So nowadays we have it extended for arbitrary propositional syntax and also arbitrary first order sentences. So you can write a first order theory and it has stable models. Right? This is something nice. How does it look like? Well, in here and there, you have interpretations that are pairs of sets of atoms. Here and there, the pair the set here is included there. For instance, you could have something like this. PQ is here, PQRS is there. But the meaning we have for this nowadays is not probably the meaning that Heiting or Gödel was using, but the meaning we have for this is as follows. Whatever is not there is false. What is included there can be assumed. It's a good assumption. You can make this assumption. But from all those assumptions you make, so only some of them are proved, let's say, or really true, right? Note that we don't assume something, no, the other way around. And everything that is proved can be assumed, right? But if something cannot be assumed, it cannot be proved, right? When H is equal to T, you have a classical interpretation because everything can be false or proof. There is no intermediate value, right? And satisfaction of formulas goes like this. We will use the pair HT, but when I use H smaller than T, I read it as alpha is proved, whereas if I use the same component in both, the same set in both components, I'm saying that alpha is assumed. And it's the same that saying that alpha is satisfied by T classically. So anatomy is proof if it belongs to H. Conjunction as disjunction is as always. Implication is the tricky thing, as in any intermediate logic, because it has two conditions. The first one could be more or less something like a modus ponens, where if alpha is proof, then beta has to be proof. So you do it there in the definition. You impose that condition in the definition, but also the assumption you make has to be coherent with the implication. So if you made an assumption, it has to satisfy the classical implication as well, right? So this is the strengthening of the implication. You have these two conditions. I think you have a question, but I don't know. Yeah, by the look. Oh, no, okay. Is it confusing?
I once started a book of logic, but never got that far. So I see some things I heard.
Okay. No, because we're looking like this has to be wrong. Maybe, yes. Negation is just derived from implication, as in any intermediate logic. So, yeah, 10 minutes. Okay, then we are going. Okay. There are several properties I will just skip. The thing is, how do you define an equilibrium model? An equilibrium model is total. So in the end, you use this logic just to see which classical logics you like, right? So among the classical logics of your theory, you select some classical models that there is no way to replace the assumptions by a smaller set of proven things. So all your assumptions have to be proved. There is no intermediate state where some assumption, by some reason, you couldn't find a proof for it, right? And this is the key idea of the thing. This is why it is an equilibrium or a state. So all assumptions are eventually proved. This is the thing. This is a table of comparison between the classical logic and the stable reasoning thing. Negation here is not classical negation anymore. Forget about it. When you say not P of X, in classical logic, you are saying that P of X is false. Here means it cannot be proved. It's not a good assumption, right? When you don't have information on P of X, in classical logic, you would get any possible model. I don't say anything about P of X. All possibilities are chosen, right? Whereas here we have a closed wall assumption. I don't say anything about P of X, therefore I cannot prove it. So it will be false, false by default. Predicates are extensional. And here, in stable reasoning, predicates can be intentional. You can define them using inductive definitions, for instance. Inference is monotonic. So if I have a knowledge base, any conclusion I have, if I add more information, I will keep it forever. Whereas here, if I have more information, I can retract something I derived before. In problem solving, it doesn't work in the same way. Normally, in predicate-based, if you use predicate-based classical logic, problem solving is a solution is some tuple for some predicate. It's a term. It's an element of the domain. That is your solution. Whereas in stable reasoning, which is a generalization of, as I said, programming, a solution is a model. And that is a quite different way of thinking. Just to put a classical example here, you would like to find the Hamiltonian paths in a graph. So essentially, you will look for a cyclic. It's like the traveling salesman problem, but without the distances. You have to visit all the nodes in the cycle. And here you have two solutions. How would you model that using classical, or let's say, first order sentences? In classical logic, in order to say which nodes do you have to write this thing. Don't forget about that. You have to say node of x is true if x is equal to 1, 2, 3, or 4. And you see if and only if. Those are the nodes. And in order to say those are the edges, you have to build this sentence here. I now know that the audience is mostly ASP, so we are so used to just giving the facts about the graph that we have forgotten this. The classical logic is not like that, right? Because we have closed goal assumption is that we can use it as a database. And we can just give the facts about the graph without saying anything else, because 1, 1 is not an edge, because it's not included there, right? So this is important because if we have new edges, we don't have to change this formula. That would be crazy, right? What happens if you want to remove the closed goal assumption? Well, this is always possible, but you have to use an excluded middle action, saying that either, which is removing the intermediate thing, right? Either it is proof or it is assumed. And then you don't have this situation in which is assumed but not proved. Well, maybe I skip this because I already said it. In the classical thing, you have to encode the cycle inside the predicate. And remember that this particular problem is not representable in first order logic, in classical logic, because you need reachability. So there is no classical logic first order theory, gamma of G, where G is the graph, where you can entail a predicate saying, this is a Hamiltonian cycle. There's no way to encode that, right? Whereas in our case, what we do is, as I said, keep all the Hamiltonian cycles as the models of the theory. And here you would have a representation where each edge, for each edge, you have, you remove the closed goal assumption for the predicate in that will tell you which edges you are keeping, right? So you are free to choose whether to keep an edge or not. This is the excluded middle action for choosing whether to include the edge in your graph, in your path or not. These two expressions are just saying that you have an unique outgoing edge and unique incoming edge. So essentially you can be linear things. And the only thing you miss is that you have to connect all the things together, right? Because you could have several linear paths that are not connected. And this can be reached by a predicate reach, that is the transitive closure of the edge, the in relation. Why does the transitive closure works? Is because whatever is not derivable here is false. That is essential. Since we have this closed goal assumption, this inductive definition works. If not, then we would also have to say what is not reachable. And this is the problem we have in predicate calculus, right? Finally, we can include a formula that would be, in ASP, this would be a constraint. Any negated formula in first order equilibrium logic is a constraint. That is saying that there are no pair of nodes that are not reachable, right? This formula is very different in equilibrium logic from this other one. Both are classically equivalent. If you apply the Morgan there, you see, you have the antecedent and the negation of the consequent, then it is equivalent to the implication below. But if you write this formula in equilibrium logic, it's not what you want, because you are saying that for any pair of nodes, all of them are reachable because the implication actually derives information. It's not material implication, okay? This is an example of inertia. Because in quantified equilibrium logic, you can use functions that have a value. These functions can be partial. So inertia can be represented as easily as that. If you have a fluent f that at time point t had value x, and you cannot prove that at time point t plus 1 will have a different value from x, then it has the same value. It's quite readable sentence if you look at it and think about all the ways in which inertia have been represented, right? Okay, so our particular work was extrapolating this same idea to other logics. What happens in the temporal case? Well, we work in temporal equilibrium logic where you still keep the propositional part, but then rather than having predicates, what you have are modal operators from the linear temporal logic literature. So the idea here is you take, this is our normal methodology, is you take here and there and you make the extension there, and then you define the model selection criterion. So you have temporal here and there, and then you select minimal models there. And a trace in linear temporal logic looks like this. It's a sequence of states. A trace in temporal here and there is a sequence of pairs where you have some assumptions and something proved, right? Some of them are classical in the sense that there is no intermediate value. Everything is either false or true. The satisfaction of formulas, I'm not going to repeat it because it's orthogonal. In order to interpret the propositional connectives, you use the jump between here and there, the here trace and the there trace. But when you have a modal temporal connective, then you play with the position in the trace you are using, right? So if you have a box, this means always. So it will be a for all the time points greater than I, and you repeat the same test. A temporal equilibrium model is exactly the same condition. It has to be a total trace. There is no assumed part that is not proved. And there is no way to build a trace that is weaker, let's say. Let me put an example. This is a formula in linear temporal logic syntax. The syntax is the same as anything in linear temporal logic. But what happens if we use temporal stable models or temporal equilibrium? The sentence is saying something like this. I have a presented test, maybe a COVID test. And forever, this means always, if I have a presented test and I don't remove the test, the present, then in the next state, it will be presented again, right? It's a kind of inertia rule, but only for keeping it present. And I have an additional formula that says, at some point in the future, I don't know when, I'm going to remove the present. What will happen here? Well, you can see it as an ASP program where you have the box is saying always. So it's like having an infinite set of rules that look like that. P and not R imply next P. Next P and not next R imply next P, and so on. So you have infinite copies of this rule working there. And the diamond is a bit like an infinitary disjunction. Of course, we don't have infinitary things, although there is a semantics for that, but we don't have it in ASP. But it's like a big OR saying, okay, you have to choose one of these options. Either you remove the present now, or maybe tomorrow, or the day after tomorrow, and so on. So the effort here is as follows. From all the possible models you would have in linear temporal logic, the models you have here have this particular shape. You have a prefix where the present is closed. At some moment, you remove the present, and then from there on, everything is false, right? Which would be the expected behavior if you read the formulas as rules. You see the point, no? Okay. Well, we have work in foundations, expressiveness, computation. We have also extended these formulas to cover regular expressions or metric expressions. In this case, I wouldn't say that we had much of a problem in this methodology of going up and down, because we took equilibrium logic, we took linear temporal logic, very well understood. We mix both things together. Of course, there are things where you can parameterize. So some mathematicians taught me, why would the interpretation of the semantics be orthogonal? Why don't you have operations where you both move the time point and the intuitionistic component? That is an option, but for what? I mean, you can do a very pretty nice formalization of ASP temporal domains already using this. So it seems it's a good choice, right? Another case, this is the second case, and I will finish, in which we apply this methodology is in epistemic answer set programming. Here, what we have is a pair of operators, K of P, meaning I know P, that actually means P is true in all the answer sets, and M of P, meaning that P is true in some answer set. And of course, the tricky thing is that you can use these operators inside the logic program that builds the answer sets. So it's kind of a self-referring loop, because in order to know whether Q is in answer set or not, I may have a condition that is saying it depends whether P is in all answer sets, and maybe P depends on Q. So you can build quite paradoxical programs there. Yeah, but the thing is that it's not what we normally think when we talk about epistemic reasoning, where we think about several agents. No, it's for formalizing a single agent that is an introspective agent, is talking about his own knowledge, let's say. The complexity is higher. The problem here is that there are different semantics in the literature. This is still an open topic. So if you want to struggle with it, or provided one more semantics, then maybe we kill ourselves. But the thing is that the methodology there is example-based. So you have a bunch of examples and you say, okay, they look counterintuitive or not. In fact, I think in Carl thesis, I remember that he has something like 80 examples in the thesis. That's quite a lot to see whether all of them agree with your intuition or not. So it's a hard task. It's something really hard to know. You have the top down because you have many of them. You have the bottom up because you have many examples. But what we propose is that let's study properties. Maybe the properties is not what you like, but it's good to know whether the property holds or not, right? We know that the stable models do not satisfy several properties. But since we know it, we know that we cannot rely on them. Like, for instance, relevance, right? If I make a query, if a stable models were relevant, only the part of the theory related to the query will tell me if there are stable models or not, and this is not true. But we live with it, and we know that the property doesn't hold. You cannot trust on it. So this is the same idea. We propose several properties like splitting, or like foundedness, or constraint monotonicity. At least let's classify the semantics in order to know whether they are reasonable or not. And then we decide what properties should be more suitable. Well, these are the two examples. I don't want to make the talk longer than, possibly much longer than expected. So the conclusions are that knowledge-based AI, especially logical knowledge-based AI, is a good candidate for intelligent interaction with computers. It allows automated reasoning, it allows declarative problem solving, and it's based on correctness. That, I think, is the key point. Whenever you have a discussion, if the word correctness is relevant, you have to move into something like this, right? New forms of logical automated reasoning enable new forms of human reasoning. I don't know if you are aware of that, but if I build a proof in temporal logic, for instance, it's valid for humans, even though the computer is not involved. And it's something we didn't have before, and we can use. You see what I mean? Right? So it is worth only if it is only for that. And the challenge, of course, you can imagine, is what to do with knowledge-based AI and machine learning as used today. You have this, I heard this to Georg Gottlob saying several times, right? We have this idea of fast thinking and slow thinking, how to combine that. And we should have something similar to what happens to humans, right? From fast to slow. Well, you should be able to, from what you do by intuition, extract new knowledge, find out possible causal connections, and express it as new knowledge to other people, right? So it would be nice that the computer came out with a conclusion, I don't know, that lighting a match causes fire, if I didn't tell it, or maybe that something causes a given particular illness or something. No? So I get the knowledge the computer has acquired. And once I have it, I can communicate to other humans, not only to computers. This is from fast to slow, but also from slow to fast happens all the time. We humans do this. The first time we reason which is the best route to get to the cathedral, but if I repeat it continuously, I don't think, I go, right? I'm not using the map anymore. That's it. So this has to happen, and this interplay should be completely connected, not something that you do from time to time. That is I guess the real challenge for artificial intelligence. So sorry for being so long. Thank you very much.
Thank you very much, Pedro, for this very nice talk. It's always good to see our daily research in the big picture, so I liked it very much. But we have time for a few questions, by the way. And maybe I started. I have one question, Pedro. So you mentioned that in the very beginning of your talk, now that in the linguistics domain, now this term now, what was it? Language shapes thinking is not true anymore. Now I know that it's not your research, but I'm just curious why they say this, because my idea was always that language is very important. I mean, when we have small children, we tell them stories or fairy tales, and this trains their brain. They imagine these stories in a kind of a real world like setting. So I always thought that language is very important to shape thinking. So why are the linguists not on this?
Maybe I'm giving the wrong answer because I'm not a linguistic either. But it seems that the accepted hypothesis is that the grammar is something, let's say, common to all languages. So languages are based on some kind of grammar, let's say. Not right, it's not something that. But the original hypothesis was based on, again, it has been debated and argued that this was not right, but it was based on the idea that the Eskimos had like 20 different words for the snow. And for them, those are not the same thing. So the snow that you find in the ground is not the same that the one you find in somewhere else, right? Whereas for us, it's just, especially for the Spanish, you see, the snow is something, oh, that thing white. And also remember something like, I think the old Greeks didn't make a distinction between blue and green. It was actually different kinds of the same color. So I wouldn't say, I'm not a linguistic, I wouldn't say that language shapes completely thinking, but at least the ontology, yes, because possibly you have a grammar, possibly you make the same structured reasoning in all the languages, but the ontology, it has to be effective for sure. Because, I mean, in German, you have so many words for differentiating between the same thing in Spanish that I'm quite impressed about.
I'm not sure what you're referring to. It's only in Vienna where we have many words for coffee, not in German. So questions, more serious questions than mine.
Oh, okay, sorry. Yeah, first of all, thanks for the talk. As I'm not very familiar with epistemic ASP in particular, I was wondering, you had a result there that satisfiability is in sigma 3p. Does this epistemic ASP include disjunction, or is it like, and this was referring, of course, to epistemic ASP with disjunction, right? Mm-hmm. Okay, that's basically it. Thanks.
Okay. Further questions? Tommy.
Thanks, Pedro, for a nice talk. So right at the end, when you were talking about the real challenge being how to link up the logic-based systems or knowledge-based systems with machine learning, moving from thinking fast to thinking slow and the other way around. So yes, I think most people agree that that is the real challenge. Working, I think, both in machine learning and the knowledge representation or knowledge-based areas. But given the area of where you work in, can you perhaps say a little bit more about what's being done at the moment to bring these two areas together? Is there any specific work in that direction, and then what's being done?
Yes, there is a connection to inductive logic programming, which was the origin of inductive logic programming is learning a prologue program from the data. But nowadays we are studying how to build tools on the inductive logic programming that learns an ASP description. I think this is important, but it has some challenges, some tricky challenges. It is important because ASP is a specification language. Although we say ANSYS programming, there is no program. There is no idea of control of flow, no ordering, and there is no timestamp for any instruction. So it is a specification language. In that sense, I think it is closer to gain knowledge because you get a specification. The tricky thing is that ASP is model-based. So one of the important things that we have recently discovered is that the way in which you provide the examples is tricky as well. Because for inductive logic programming, you would say, this is a positive example, this is a negative example. That's it. But here you have to say, this is a positive example in one answer set, but not in the other. This number is here in one Sudoku, but not in the other, right? So there are no answer sets contained in this. There are some answer sets that contain this. So it's more complicated. And regarding efficiency, well, still we have to be aware that it is a different kind of learning. Inductive logic programming is good for small data sets, but can give you very valuable information. I think Muggleton had an example where they were able to extract a set of rules to classify a given treatment from the data. This is being used for the humans. So imagine the power of this. I give you a set of rules that now the doctors can read in natural language and apply. So the classifier we got are the humans. So that is something I think really interesting. But yet we are not in the point of using big data for something like that. It's not like that.
Thanks.
Okay, so I think we would have time for a final question. Clement?
Thanks. So coming back to fast and slow thinking, machine learning and knowledge-based AI. One of my favorite examples is this expert system MySyn that provided doctors with rules which antibiotics to apply given or finding out, estimating some bacterial infections, right? And it worked amazingly well. It was tested, right? And it performed at human expert level even. And that was kind of a one-off implementation in the beginning, right? Using lots of probabilities. Right? And the second point is in machine learning, the best results that we can have in a certain sense are probably approximately correct estimates, right? So with a certain probability, the error is at most this large. So if these two points in mind, to me, it seems that the connection between machine learning and knowledge-based AI would somehow be related to probability. So where do you see the role of probability between ML and knowledge-based AI?
Well, probability is a whole different story in the sense that we also have these two readings of probability, right? The statistical reading and the epistemic reading. So, for instance, I think that probability is very connected to epistemic reasoning. But normally, the way in which we use probability is the statistic-based one. And yes, at some point, we will have systems that we cannot be sure that it's correct anymore because we don't have the real interactions in the system. And maybe there is no way to find them, right? So you are analyzing a system, you learn from it. The human body is not something that you expect to have a model, like a rigid model that is going to work like that. Probabilities is something you need. The risk there is, at least the one we are facing when we do things like that, is how to differentiate between statistical correlation and causality. And that is something really, really hard, even for inductive logic programming thing. It will have the same problem because what you learn is a classifier, right? And let me put this, there is this joke of the guy that goes with the bomb in the plane, right? And says, why do you get a bomb? Because the probability of having two bombs is so high that I guarantee that I will never have two. So it's confusing correlation. What happens with causality? Having a bomb will cause that the other guy will not bring one. And this is really, really difficult to differentiate. This is why I said probability, yes, but for sure, causality has to be there. Probability has to be interpreted. Why I got this result? What would happen? Use a counterfactual. What would happen if I change the experiment? And which result would I get? And that is also a tricky thing because causality is something really hard to study.
All right, so I would say let's thank Pedro again. Thank you very much. And we now have 30 minutes for coffee around. We continue at 4 p.m. That's the more precise statement.
Hello.
Hi, how are you?
Now feedback or?
Hello, welcome
Hi, how are
to
you?
Vienna remotely.
Thank you for organizing everything.
You're welcome. We do a quick sound check if you come across good, and otherwise make you quickly the host so you can share your slides.
Okay, let me the sound is good, right?
Sound is
Okay,
really good.
let me also share the slides and
Yes, look good.
is it good?
Looks good, yeah.
Okay, let me, yeah, I can also move it. That's great.
I'm just asking you if it's okay for you if we record the session, so it will be like on the website.
Sure.
Later on.
Sure.
Cool. And the session will be then live streamed for some colleagues who like can't come to location. I can shortly try to show you the audience. And in the background, you could see Vienna, but I think my webcam is like too sloppy.
No, yeah, yeah, hopefully I'll be there in end of July. So
that would be lovely.
Yeah.
So we have like 7 minutes till to go.
Sure.
And if you have any questions, just let me know. Otherwise, I think we are from the technical setup done.
Okay, great. Thank you very much. I appreciate it.
I have to say thank you.
Okay. Okay, das ist okay. Hi, Mohammad.
Hi, how are you, Thomas?
Hi, I'm fine, thanks. How are you? Don't know if you can see me. Ah, okay. Okay, now you can see me. Okay, so we'll get started in a few minutes. Thanks for being available, right? It's 7 a.m. for you, right?
Yes.
Yeah. All right, so we appreciate it a lot, and yeah, we'll start in 2 or 3 minutes.
Sure. And how do you want to handle the questions? Is it going to be at the end, or is it going to be during the talk?
We'll handle them at the end mostly.
Okay.
So we can take, we have a microphone here in the audience, and Walt is going to watch the chat, and he will relay the questions by audio as well. So you don't have to look at the chat or anything.
Okay.
All right. All right, it's 4 p.m., so we'll get started with our second talk. That's the Machine Learning Colloquium talk, live from California. It's a pleasure to introduce Mohammad Ghavamzadeh, whom I'm sure several of you know from his publications in reinforcement learning, mostly from policy evaluation. In his colloquium talk, he will talk about handling constraint in Stochastic Bandits. He received his PhD from the University of Massachusetts in Amherst. He was a postdoctoral fellow at the University of Alberta, a permanent researcher at INRIA. At INRIA, he received the Award for Scientific Excellence in 2011, and he obtained his habilitation in 2014. Since 2013, he has been a senior researcher at Adobe and FAIR, and he's now a senior staff research scientist at Google. He has published over 100 refereed papers in machine learning, major machine learning, AI, and control journals, and in conferences. He has co-chaired more than 10 workshops and tutorials at NeurIPS, ICML, and AAAI. His research has been mainly focused on reinforcement learning, bandit algorithms, and recommendation systems. Mohammad, it's a pleasure to have you here today, and we appreciate it even more since we know how early it is for you in California. So please go ahead.
Thank you very much for the introduction, and thank you for the invitation. So the talk today is about constraint in stochastic bandits. I'm going to talk mainly about two problems that we have been working on in the last couple of years. Some of these problems have been also extended to reinforcement learning, but today I'll mainly focus on bandits. So this is the outline of the talk. I'll give you a brief overview of multi-arm bandit and linear bandits in case some of you who may not be in the audience might not be familiar with the details of these topics. And also I need to establish the notations for the main part of the talk. And then in the second part of the talk, I'll talk about two bandit problems with constraint, which I call the first one conservative bandits, and I'll define it as we move forward. And then the other one, I'll call it the linear bandit with linear constraints. And again, I'll make it clear as we move forward. So let's start with multi-arm bandits. So K-arm stochastic bandits is a problem or a game in which we have capital K arms. Behind each arm, there is a distribution that I use P1 to Pk as the distribution of the arms. And each distribution has a mean that I use mu1 to μk as the mean of these distributions. Of course, the best arm is the arm that has the maximum mean, mu star. And each arm has a suboptimality, which is the difference between the mean of that arm and the mean of the best arm. And we call it gap or suboptimality of the arm. The game plays in rounds, and capital T, I use it in this presentation as the number of rounds that this game is played. At each round, little t, the learner or the agent selects an arm, we call it IT, and then when you select an arm, you sample a reward from the distribution of that arm called RT, and the goal of the learner is to pull the best arm, the arm that has the maximum mean, as many times as possible during this game T. But of course, since the learner doesn't know which arm is the best arm, then the whole interesting part is to discovering the best arm. So the goal, as I said, is pulling the best arm as more as possible, or equivalently maximizing the cumulative reward that you receive, or minimizing something called regret. And regret is defined of this form. The regret at time for T rounds game is the difference between the average reward of the arms that the learner has played and the average reward of the best arm. So if you knew in advance which arm is the best arm, you would have played the arm with mean mu star, and your total reward was capital T times mu star. But since you don't know, you have played other arms, and you have received the sum of the mu t's that you have played, and the difference between this is your regret. And a learner is good if we can basically make this difference not to grow very fast with capital T. So this regret cannot be zero, because eventually you need to learn which arm is good, but you want this learning in a way that gradually you find the best arm, and basically you don't lose anything from some time on. And this regret should not grow rapidly with T. You can also write this regret in a different way. Another way that you can write this regret is you can basically say how many times I play a suboptimal arm, and every time I play a suboptimal arm, the amount of loss that I suffer is the suboptimality or gap of that arm. So this regret can be also written in terms of the gap multiplied by expected number that you play a suboptimal arm, which I use this capital T or curly T to show. Okay, so this is basically the regret decomposition. And as you can see, the goal is regret minimization in this game. So of course, for the agent, in order to identify the best arm, usually they are looking at some statistics of these arms, and the most obvious statistics is basically the empirical mean of the arm. So the learner basically, whenever it pulls an arm, it calculates the average of that arm, or the mean of that distribution of the arm. So mu hat show at time t for arm I shows the empirical mean of that arm up to time t calculated by the learner. So one of the very popular bandit algorithms is called upper confidence bound or UCB style algorithms. So for UCB style, at each round, the agent calculates the empirical mean of all the arms. It calculates an interval around this empirical mean mu hat, which with high probability contains the true mean. So this interval, as you can see in the slides, I hope you can see also my mouse. So this is that interval. So now this upper confidence bound or optimistic exploration is in a way that the agent plays the arm that has the maximum upper bound. So this B, which is the like the identity at time t for each arm k, is the upper bound of this interval for arm k. And we play the arm that its upper bound is maximum. So this is like the optimistic view, or upper confidence bound name is coming from there. So this is the main idea of UCB. You calculate some statistics of the arm, you estimate an interval that with high probability contains the true mean of that arm, and then you play optimistically. You look at the upper confidence bound and you look at the arm that has the maximum. So basically you are greedy with respect to the upper confidence of each arm. And it's well known that the regret of UCB algorithms is of this form of root square of kt log t. So now when we go to linear bandit, when we have more than the number of arms starts growing, we need to be able to kind of generalize over the arms. When we have k arm bandit, usually there is no generalization between the arms. By playing one arm, you don't learn from the other arms. But when the number of arms grows, if there is no generalization, probably in that case, learning becomes very difficult. So we need to assume some structures in the reward that we can generalize and say, okay, if I pull this arm, I can also learn something from about the other arms. So this linear structure basically helps us to learn in cases that the number of arms is very large or even infinite. So let's see what is the stochastic linear bandits. I put contextual in parentheses because you can always assume that there is also a context, or you're assuming that there is no context and you're just picking among the arms. So the game is of this form. Again, the game is played in 3 rounds. At each round, the agent first observes a context, xt. And as I said, if the problem is not contextual, you can just eliminate this item and you don't see any context. But let's say in advertisement, this context is the user that comes to the website. And then the agent should select an action, and you can say, I want to show you an ad, and this action is which ad I'm going to show you. And then upon showing this action to this user, you receive a reward function, which you can think about whether user clicks on it or user purchased that item or something like that. So this is the reward that you receive. And this reward has an expected part and a noise. And the linear structure comes from the fact that we assume that this reward has a linear structure. And this linear structure means the mean of this reward is an inner product between an unknown d-dimensional vector theta star and a d-dimensional vector that represents this arm, which is the feature of this arm. Of course, when we have context, this is feature of the context and the arm. If there is no context, it's just the feature of the arm. So each reward of each arm has a mean, which is the inner product of an unknown parameter theta star and the feature of that arm plus some noise. Okay? And then the regret in this case is defined as the difference between the optimal, the mean of the optimal action A star, which is at each round. If we assume that there is a action set at each round AT, you can have the best action, and best action is the one that is most aligned with theta star. That's the base, and AT is what you have played, and the difference between these two is your loss in that round, and the regret is some of these losses. And as you can see, the regret is in terms of the similar to the multi-arm bandit case, is in terms of the mean of the reward. This expected that this inner product is the mean of the reward, and there is also a noise that is added. And what the agent observes is this noisy version. What viewer is evaluated at is the mean. So this is standard in both multi-arm bandit and linear bandit. What you observe is the noisy reward. What you evaluated for is the average of that reward, is the average or the mean of the reward. Okay, so this is the formulation of the stochastic linear bandit. The idea of the UCB style algorithm in linear bandit is also very simple. The idea is of this form. What is unknown is theta star. If you know theta star, the problem is solved. You find the action that is the most aligned with theta star, but you don't know what theta star is. So you always construct a confidence set, which I use this capital theta for it. At each round T, you build a confidence set that with high probability contains theta star. And this confidence set, as you can see, has an ellipsoid form. So when I say like we construct an ellipsoid, this is basically a space that contains with high probability the unknown theta star parameter. And what is the center of this ellipsoid is the solution of the least square problem. So you basically, given the observation that you have had, remember the reward is linear, so you solve a least square problem. This gives you theta hat star. This is kind of like the equivalent of the empirical mean in the that we were computing in the multi-arm bandit case. Around this, you build a confidence set that with high probability contains the theta star, and then when we want to take an action, you take an action in your action set that again is optimistic, meaning that in the set theta t is the most aligned with, so you take an action that is the most aligned with the best theta in theta t. So you do a max problem here. So the action that is the best aligned with a parameter theta in the feasibility set or the confidence set theta t. So this is the standard algorithm that you play. At each round, you build the confidence set, or and then you solve a max problem. Okay. Of course, depending on the shape of this AT set, this problem, this max problem, can be solved easily, or it might be hard. Depends on what is the shape of these actions. And the regret is root square of t log t, and d is the dimension of the space, dimension of the theta star. Okay, So this is the UCB algorithms in both linear bandit and multi-arc bandit. So now let's go to the R problems, the constraint problem. So far, I hope I explained what is multi-arc bandit, what is linear bandit, how the UCB style algorithms work in these two areas, and also I hope I established the notation that I'm using throughout this talk. So now let's go to the constraint case. So in the constraint bandit, the learner still is minimizing its regret, but while it's minimizing its regret, it should satisfy certain constraints. So constraints, I can classify the constraints in two forms. One of them, I call them history-dependent constraints. The history-dependent constraint, the constraint at each round depends on everything that has happened from the beginning up to that point. So basically, the quantity that we put the constraint on is a quantity that depends on everything that has happened from the beginning up to that round. This is what I call it history-dependent constraint. The stage-wise constraint, on the other hand, the constraint at each round depends on what is happening, or a quantity that only depends on what's happening in that round. Okay, so for example, I give you some example. So let's imagine that you have a budget that every time that you pull an R, you receive a reward and you consume some budget. In that case, whatever happens at round T is not only depend on what happened in round T, it depends on the entire history from the beginning up to that point, because it depends on your whole budget consumption. But sometimes the constraint is on certain quantity of the arm that you pull. For example, its variance is some quantile of that arm or something like that. So this is a constraint in which history doesn't play any role. Whatever you do with that round defines the constraint. So this is the difference between stage-wise and history-dependent constraint. For those of you who are more familiar with this literature, an example of history-dependent constraint is knapsack bandit. In knapsack bandit, every time you pull an arm, you get a reward and you consume some budget. And the goal is to maximize your cumulative reward before you run out of budget. So this is the standard knapsack problem. And it's a very good example of history-dependent constraint. The other problem is the problem that I'm going to talk about in this presentation, the first part of this presentation, and I call it conservative bandit. In conservative bandit, there is an arm, or there's a strategy called the baseline strategy. And on each round, you want to pull an arm such that your cumulative reward from the beginning up to that point is within an alpha fraction of the performance of the baseline. So therefore, the constraint that you have at each round T is a constraint that depends on the entire history, because you look at your entire performance from the beginning up to this point, and you compare it with this baseline, and you want to make sure that you are close enough to this baseline. And I explain the motivation behind this formulation as we go forward. On the other hand, for stage-wise constraint, good examples are risk-sensitive bandits. As I said, you want to pull an arm that has a large mean, but you don't want the certain quantile or the variance of that arm is too large. Or in that case, the constraint only depends on the action that you take at that round. Or the problem that I'm going to talk about in this talk, which we call it the linear constraint bandit. In this case, you can assume that behind each arm, there are two distributions, one for the reward, one for the cost. You want to pull the arm that has very high reward, but you don't want to pull an arm that its cost is above certain threshold. So basically, you're dealing with quantities of two distributions, and you may have an arm that has very large reward, but may have also bad cost. So therefore, you have to trade off for that. Okay, so this is a scenario that is also, and this has application in the sense that you may show, for example, I give you an example of such scenarios. I may show you an ad or show you some content that you definitely watch it, but it's so disgusting that you never come back to my website. So the reward is high because you watch it. The click rate is very high, but it's so bad that you're not going to come back to my website because it's very offensive or something like that. So this is a good example of this scenario. Or I give you a drug that helps you in a short term, but has a long effect, or that you're not going to come back to me as a doctor or take that drug again. Or you can think about the multi-objective problems. In multi-objective problem, you have certain objectives that one of them is very important. The other one, you need to control them. For example, one you want to maximize, the others you want to control to remain in certain boundaries or be less than something. So this is another example that happens a lot in practice, that you have a multi-objective problem. Some of them you need to make sure that remain below certain thresholds, and the other one you want to maximize. So this is, again, example of a stage-wise constraint. Let's start with the conservative bandits and go a little bit to the details and see how we deal with this problem. This is based on two work that we have done in 2017, and then we did a nice update of that work and improved the algorithms and analysis in 2020. So these are the two papers that this part of the talk is about. So the motivation behind this problem that I actually got to it is related to deployment of strategies. So when you want to deploy a strategy in a company, usually company has a baseline performance. Your strategy is pi, the company's strategy is pi b, the baseline. And usually when you want to convince them that your strategy is good, they basically run these two strategies in parallel. They, of course, at the beginning, they give you a very, very tiny fraction of the traffic, and then they keep checking the performance of your strategy and compare it with the baseline. If the strategy has very, very bad performance with respect to a baseline, they stop the test and they say, okay, your policy, your algorithm is not good. But if your algorithm performs similar to the baseline or better, they give more and more traffic to your algorithm, and eventually, if it remains still better than the baseline, eventually they deploy your algorithm, and that becomes the company's strategy. So now, if you have an algorithm that is explorative, and a lot of machine learning algorithms have this form that they explore, at the beginning of the game that you explore a lot, your performance might be very bad because you're trying things that are very that are unknown. So if you explore too much, this system stops, because at some point they see that your performance is really bad with respect to a baseline, they stop and they kick you out. But if you control your exploration and make it a little bit conservative, and how much conservative depends on how sensitive this problem is, or how sensitive that manager is in terms of how fast he panics, right? Then you can stay in the system longer, and eventually your algorithm reaches its final performance, and let's say it's better than the baseline, it's going to be deployed. So the whole idea here is to make your exploration more conservative, given the amount of sensitivity of the manager or the system. This way you delay your learning. Basically, your learning takes longer, but you don't make anybody panic. You remain in the system. Eventually, you reach your final performance, and your final performance is good enough that your algorithm becomes dominant and is going to be finally deployed. So this is the whole idea of this, how to control our exploration with respect to the sensitivity of the system. And this is why I call it conservative exploration. So let's see how we can formulate this problem in the context of linear bandits. This is the formulation of linear bandit. I already explained it to you. Just refresh your memory. As you can remember, here there is this theta star parameter that is unknown. The action that you take has this feature. The reward that you observe is the inner product of this feature with this theta star plus some noise. And this is the definition of regret that we define. So now, the difference in conservative case is there is this extra baseline. There is a policy, I call it pi b, and pi b is the strategy of the baseline. And in Bandit, you can think of this baseline as a certain arm or certain strategy over arms. And the BT is the arm that the baseline strategy selects at time t. So at each round, the expected reward of the baseline is theta star time this. And your performance should be compared with this. So let me see how it compares. So at each round t, what is your performance? Your performance is I equal 1 to t of the reward, the average reward of the arm that your algorithm plays. What is the performance of the baseline? Is I equal to t, is 1 to t of the average reward of B, of BI. So the difference between these two is the amount of loss that the company suffers by letting you handle certain portion of the traffic versus they would have given it to the baseline. If this difference, this loss, is less than an alpha fraction of the performance of the baseline, this is good. If it's not, then the manager is going to panic. And this alpha is basically showing how sensitive this problem is. If you're talking about drug and medical field, probably this alpha is very, very close to 0 because the tolerance of error is, we cannot tolerate too much error. But if we're talking about advertisements or some other problem, maybe this alpha is close to 1 because the sensitivity is not that high. So this alpha plays between 0 and 1. 0 means the problem is hard. You have to be very careful. 1 is basically unconstrained problem. And we go back to the standard unconstrained formulation. So this is how we formulate this problem. I can rewrite this constraint by just simple algebra to this form. So why I wrote it in this form? Because I want to show you something. So what is important here is every time that you play the baseline, the left-hand side of this equality gets the reward of R bar B. The right-hand side gets the reward of 1 minus alpha R bar B. What does it mean? It means that every time that you play a baseline, you gain some extra budget to now do something else. So what does it mean? It means that since you don't want to make a mistake, you play the baseline, you play conservatively until you collect enough budget of doing error, and then you can go and try another action. And if that action is bad, you have some budget to consume, right? So this is how this game is played. At the beginning, you don't know anything. You play baseline. You get, according to this fraction, you get some budget of exploration. Then you try a new action. You learn about a new action, and you try second new action. So it's basically a game that you play between being conservative and being explorative. So every time you're conservative, you gain some budget to be explorative. But of course, if alpha is very close to 0, the budget that you gain is very, very small. And the game is hard. Alpha is equal to 1. Every time you play baseline, you gain a lot of budget to explore, right? So this is how this game is basically played. And the problem is of this form. You're still doing regret minimization, but at each round t, at each t, you have to make sure that this constraint is being satisfied. If this constraint is not satisfied, the manager panics, the game is over. So you have to make sure that this constraint is satisfied. So this slide is a little bit messy, but the idea is very simple. So what is the idea of this algorithm? The idea of this algorithm is at each round t, similar to the unconstrained case, we build a confidence set that is that ellipsoid that with high probability contains theta star. And then we come and calculate which actions are feasible. Remember, in unconstrained case, all actions are feasible and iterable. In constrained case, we need to find which actions are feasible. In order to calculate the feasibility of the action, we have to come to our constraint. Remember, our constraint is of this form. Okay, so we know what happened from the beginning up to time t-1, but we have to guess about what will happen at time t, and according to that, see which action is allowed or we're not allowed, right? So look at this. So the SCT-1 are all the rounds at which you have played the action suggested by the baseline. So these are the rounds that you have been conservative. And these are the rounds at which you have been explorative. ST-1 is the set of all actions that is different than the baseline. And for the round T, you say each action, I look at the worst case performance of my action, and then see if according to the worst case performance, the constraint is still satisfied, this action is a feasible action. If with the worst case performance, the constraint is not satisfied, this action is not feasible, it's out of my constraint set. Okay? And in order to calculate this feasibility, we need, because we don't know what is this theta, we need to bound this, and we are using this Friedman inequality, and I don't want to go to the details, but what is happening is this gives us a way to calculate, because you want to calculate the worst case performance of your action. So you need a bound that to use for the worst case performance of all possible actions and see which one is feasible. So we are using this Friedman inequality, which is a tight bound and helps us to not to be too conservative. And here we are assuming that the performance of the baseline is known. If the performance of the baseline is not known, you can always compare your worst case performance with the best case performance of the baseline. This is a standard robust formulation that you look at your worst case versus the best case of the adversary, and if you still satisfy the constraint, then the constraint is satisfied. So it's the same thing. But it's in many applications, it's reasonable to assume that the baseline is known, because the baseline is the strategy of the company that has been being played for a long time. So we know a lot about it. So it's not a crazy assumption to assume that the baseline is known. But if it's not known, you just look at the best case performance of the baseline versus worst case performance of yourself and see whether an action is feasible or not. Okay? So now, when you detected the set of feasible actions, then you do the max-max problem that you were playing in the unconstrained case. Except in that case, you were playing argmax of all actions and the max theta in the confidence set. Here, you are doing argmax over the feasible actions. And this is very important, that what if there are many feasible actions? If there are many feasible actions, we play optimistically. We play the one that has the maximum upper bound. So this is what this constraint basically says. So if you have multiple feasible actions, you play the one that has the maximum upper bound. And if no action is feasible, you play the baseline. So in that round, you're conservative. This is a very simple pictures case. Imagine this red arm 4 is the baseline. So arm 1 is not safe because its lower bound is worse than baseline. Arm 5 is terrible because it's both upper bound and lower bound is below the baseline. But both arm 2 and arm 3, they have a lower bound that is above the baseline. So both of them are feasible. And in this case, I play arm 2 because the upper bound of arm 2 is better than the upper bound of arm 3. So this is this strategy basically says. Okay, so this is basically a switch between the being conservative and playing according to the baseline and being explorative and act according to the UCB algorithm. So when we analyze the regret of this algorithm, the regret of this algorithm can be decomposed in terms of the regret of the unconstrained problem multiplied by the number of rounds that we have played conservatively times the suboptimality of the conservative strategy. Because remember, every time that you doubt, you play conservatively. So if the baseline is very bad, every time that you play conservatively, you're going to lose a lot. So this is very important. And then this is the regret of this algorithm. The regret analysis is shows that the regret of the constraint case is equal to the regret of unconstrained case, which is at the order of the root square of t log t, plus a constant. And this constant depends on delta H, which shows how bad is the baseline, and depends on alpha, which shows how sensitive the problem is. As you can see, if the problem is super sensitive and alpha is super small, this term kind of blows up. This is a very hard problem. And the other case is if your baseline is very bad, which is then every time you play your baseline, you lose a lot. And this delta H basically hurts you. But this term doesn't grow with t. And this is the good thing, that there is a hope that if the problem is not too difficult, and difficulty comes from alpha and comes from suboptimality of the baseline, then there is a hope that we can still learn this problem with some extra cost, which doesn't grow with t. That's the main message. These are some experiments that we basically show the sensitivity of the regret with respect to different values of alpha. You can see the blue is when there is no constraint, basically alpha is equal to 1. And as we make the alpha smaller and smaller, the purple one, you can see the regret is larger and doesn't go to 0 very fast. So this is normal. And this basically shows the number of constraint violations. So if you if you run the unconstrained algorithm, you can see how much you are, what is the percentage of the game that you are violating the constraint. These are the percentage of the rounds that you violate the constraint if you just play the unconstrained algorithm and don't care about the constraint. But if you play the constraint algorithm, you can see that the violation remains constant, equal to 0. I don't want to go to more experiments. And this is, again, another example that shows, look at the red algorithm. Red algorithm is, again, unconstrained. And the green algorithm, which has been covered here by red, this is the constraint algorithm. You can see the regret of unconstrained is better than the regret of constraint, but this basically shows the number of constraint violation. The red violates the constraint in the first round of the algorithm a lot, but the dotted one doesn't violate the constraint. So basically, you can clearly see that we can satisfy the constraint. Of course, our regret is going to be worse because we are delaying our learning and are more conservative. But if you play unconstrained, this is the cost or the price that you pay. You satisfy, you violate the constraint, basically. Your budget goes below 0. And this happens especially in the first round of the algorithm. The algorithm is very explorative. Okay. So I want to skip this part. And this part is basically this, that in the previous formulation, the constraint had to be satisfied at every round t. So this is very, very harsh in the sense that whatever you do, I'm going to check. But in many scenarios, I don't check the constraint at every round. I check the constraint at, I don't know, every 10 rounds or every day, every week, every month, something of that form. In that case, you have flexibility to violate the constraint in between, and therefore you can be more aggressive in terms of learning. So we basically formulated this and we provided an algorithm that instead of checking the constraint at every single step. We check the constraint at every tau steps. And in this case, you can change the algorithm a little bit and making it less conservative. Still, you satisfy the constraint, but you're going to be less conservative, and your regret is going to be much closer to the regret of unconstrained. I'm just skipping this part. I want to go to the second formulation. Sorry that I'm not in the room to have more interactive session that you can ask your questions right away. So I'm going to the next formulation. The next formulation is, as I said, is a stage-wise constraint, linear bandit with linear constraint. This is based on the work that we published last year at AI Stats, and a new version of it is has been submitted to a journal. Let's start with this problem. This problem, again, at each round T, learner selects an action AT from the action set capital AT. But as I said, behind each arm or behind each action, there are two distributions. One distribution is the reward distribution, whose mean is an inner product between the theta star unknown reward parameter and the feature of the action. And the cost distribution, whose mean is the inner product between mu star, which is the unknown cost parameter, and the feature of the arm plus some values. Okay, so I use R bar and C bar to show the mean reward and mean cost of the arm. So the actions are feasible that their expected cost is below certain threshold. So basically, you are pulling arms that have maximum reward, but their cost should be bounded by theta with high probability at each round. So you have to make sure that at each round, the action that you play is the action that has the highest reward, but its cost satisfies this constraint. So that's the game that we are playing. There, again, is a regret minimization problem. You're still minimizing the regret, and the regret is defined exactly as unconstrained case, except we have this stage-wise constraint that needs to be satisfied with high probability. Okay? So this problem is impossible to learn if we do not make an assumption that there is a safe action. Because if you don't know anything about the action, how do you want to guarantee that the first round that you play something, you're not violating the constraint? Because of this, in order to make this problem well-defined, in addition to the constraint threshold, we have to give a safe action as input to this problem. So there is, and what is a safe action? A safe action is an action whose expected cost is below the threshold tau. So if you play that action, you're not gonna violate the constraint. And the whole game is of this form, that you play this. Remember, because of this linearity, you can generalize. By playing an action, you can learn about other actions. So the goal is you play the safe action, and using the safe action, you gradually learn about the other actions, and then you start deviating from the safe action and exploring among the others. Okay. So these are the average reward and average cost of the safe actions, C bar 0 and R bar 0. So as you can see, that the closer this C bar 0 is to the threshold, meaning that your safe action is risky, safe but it's risky, then the problem is harder. And also the quality of your safe action is very important, because you're going to play this safe action a lot. Every time you don't know what to do, you play the safe action. So if the safe action is a bad action, every time that you play it, you're going to lose a lot, because this reward is very suboptimal, right? So you can clearly see that the hardness of this problem will depend on how far is this reward to the maximum possible reward, and how close is this cost to the threshold. Okay? So that's the problem. What is important is we need to know about a safe action. In the rest of the talk, I assume that the safe action, of course, you need to know, but I assume that C0 bar and R0 bar are also known. But if they are not known, then you're going to have a phase at the beginning of the algorithm to estimate them, and then you can play them. So the problem can be still solved if these two are unknown, but A0 should be known. Otherwise, the problem cannot be solved. Okay? So before I tell you about the algorithm, I need a little bit of notation. So this curly VO is the span of the safe action, and the curly VO perpendicular is the orthogonal complement of this space. And each feature in RD can be projected in both curly VO and curly VO perpendicular. And this is how you can project. Okay, so these are the two spaces, the space of the safe action, the span of the safe action, and the orthogonal complement of it. We're gonna use these two spaces in the algorithm. Okay, so now let's start with the algorithm. The algorithm has similarities with the unconstrained case, and I tell you what is the difference. At each round T, you need to build an estimator using least square and then build the ellipsoid around it. So here, the first step is exactly the same. You use the reward, you solve a least square problem, a regularized least square problem. You estimate the unknown reward parameter at time T. This is a standard similar to the unconstrained case. This part is not a standard, and it's for this case. You also solve another least square problem, and you calculate the estimate of the unknown cost parameter, but you learn its projection in the orthogonal complement space. Why? Because the cost in the span of the safe action is known. This is why you need to look at the value of the cost in the orthogonal space, in the orthogonal complement space. Okay, this is why we solve this least square problem there. So now we have two estimates: one for the reward parameter and one for the cost parameter, of course, just for the orthogonal complement part of the cost parameter. Now we build our feasibility set or confidence set. The confidence set for the reward is exactly as before. Before means in the unconstrained case, you build your ellipsoid. And now you build another ellipsoid around your estimate of the cost parameter. Okay? And both these ellipsoids, you can prove that contain theta star and contain the projection of mu star in the orthogonal complement space with high probability. Okay. What I would like you to notice that these two ellipsoids have different radius, alpha r and alpha c. So these are kind of, I call it, these are asymmetrically scaled. They don't have the same radius. And this is actually very important. I'll show you how to set this alpha R and alpha C is very important. And we basically learn how to set them from the regret analysis, and then we put it in the algorithm, right? So this is very important that these two ellipsoids should be asymmetrically scaled, and I'll explain to you why this plays a role when we get to the regret analysis. But for now, assume that somehow you know this alpha R and alpha C. But I'll tell you how we calculate it and give it to the algorithm. Then the third step of the algorithm, remember, whenever you have a constraint, you look at the worst case versus the best case. So basically, we need to look at the pessimistic cost value in order to calculate what is the feasible set. So the feasible set of actions are those actions that their pessimistic cost satisfies the constraint. How can we calculate the pessimistic cost? The pessimistic cost is calculated this way, which is the known cost along the direction of the safe action plus the maximum possible cost in the orthogonal complement space. Right? So all the actions whose pessimistic cost is still feasible are in the feasibility set. And this is the feasible action set. And then remember, the action that we take is the action in the feasible set that maximizes this. This is similar again to the standard algorithm. The only thing that has changed is in a standard algorithm, this argmax is over all actions. Here is over the feasible actions, right? And this is the optimistic reward value. These are all these algorithms are upper confidence bound. These are optimistic algorithms in terms of the reward. So this is how the algorithm works. First, we calculate the feasibility set of actions, and then we do the maximization. So now let's get to the point that I wanted to tell you why this alpha R and alpha C is important and how they should be set. When you go to the regret analysis of these problems, usually you do this regret decomposition and you get to these two terms. So this term is the average reward of the best action that you could have taken at round T, A star T. And this is the optimistic reward of the action that you have taken. In the unconstrained case, you know that A star belongs to the action set that you consider in that round, and therefore the optimistic reward of that action is better than the average of that action. So this term is always negative. And you just throw it away in your analysis because you want to upper bound your regret. But when the action set that you consider is not the entire action space, is only the feasible actions, this term is not necessarily negative, that you throw it away from your regret analysis. So now what we do with this alpha R and alpha C is we set them such that we make sure that whether A star is in the feasible action set or is not in the feasible action set, this term remains negative, and I can throw it away from the analysis. So we need to set this alpha R and alpha C in that way, and alpha R should be larger than alpha C. And this is the way that we set them. Alpha R versus alpha C is set of this form. And as I told you, the difference between the performance or the reward of the safe action and the maximum reward, in this case, you assume that the maximum reward is 1, this difference and the difference between the cost of the safe action and the threshold, these are the most important quantities of this problem. These are the two quantities that makes this problem very hard or very easy. So they also play a role here in terms of how we set alpha R and alpha C. And since these things are known, we know how to set alpha R and alpha C. So the algorithm knows everything. And then the regret of this problem, again, is at the order of d root square of t. And log t is, of course, here. It's the O tilde. So this is d root square of t. This is the regret of unconstrained case. And a term that depends on this complexity, 1 minus r bar 0 and tau minus c bar 0, and d root square of t. So remember, the difference between the conservative bandit and this case was this extra term in conservative bandit was independent of t. Here, this term still depends on t, but its growth depends on this complexity of the problem. And this quantity is the complexity of the problem. So this problem can be as hard as being impossible when or can be managed. Okay. As I said, there are. I'm just summarizing right now. So as I said, the knowledge about the safe action. So the safe action needs to be known. But as I mentioned, the reward and cost of the safe action doesn't have to be known. We can estimate them. Of course, it hurts the performance of our algorithm, but still is doable. Extension of this problem to the multi-arm bandit is impossible, because multi-arm bandit, as I said, when you pull an arm, you don't learn about the other arms. Here, the whole point is I pulled the safe arm, I learned about the other arm. So this setting cannot be applied to multi-arm bandit. We have an extension of this setting that we change the high probability constraint to constraint in expectation. That setting can be extended to multi-arm. But this particular high probability setting cannot be extended to multi-arm bandit. This setting can be extended to multiple constraints. So multiple constraint means that each arm or each action has more than two distributions, one reward distribution, multiple cost distribution, and you put constraint all these costs. You're maximizing the reward, but you put multiple constraints on the costs. So this can be handled. So this problem can be, this algorithm and this formulation can be extended to the case that we have multiple constraints easily. We have a lower bound for this problem. I'm not going to go in details. There are some experiments that I jump, and this is the relaxation that I told you to expectation, which if you're interested, you can look at our papers, and I rather to stop here and take questions. Thank you very much.
Thank you very much for this interesting talk. Are there any questions from the audience?
Maybe a bit on the further implications for the big field of AI. I understand there are a lot of applications these approaches are applicable to. So maybe could you say a few words on which kinds of problems these kinds of approaches that you introduced can be applied to?
So the first problem, the conservative bandits, as I mentioned during my presentation, the whole motivation was in deployment. Because in all big companies, the way that they usually evaluate your strategy, let's say recommendation strategy, I'm working a lot with YouTube right now. When they want to evaluate your recommendation strategy, this is the way that it works, that they run a test, they give a small portion of traffic to your algorithm, and then the rest of the traffic is handled by the current strategy of company. And then they have something that they call it rasta at Google. So rasta is basically you set a bunch of metrics, and these metrics are all relative between these two strategies, your strategy and the strategy of the company. And then they keep checking these metrics. And of course, the gatekeeper of the system or those guys, they have certain metrics in mind. And usually it's a multi-objective problem because they look at multiple metrics. But in the simple case, imagine that, okay, one metric or two metrics plays the most important role. And then they look at these values at random time. We don't know how often they look at it. And then if they see that your algorithm is really performing worse compared to the baseline, they stop the test and they say, okay, you're no good, go. But if they see that the performance is good, it's competitive, then they start gradually giving a little bit more traffic to your algorithm and keep looking at these metrics. And eventually at some point they say, okay, thumbs up, and you can deploy your strategy. So here is exactly the same form, that if you have an algorithm that is constantly learning and doing exploration, if you're too explorative at the beginning, you may basically scare the hell out of the gatekeeper of the system, because it looks that the numbers are really bad and then they stop it. But if you can control the amount of your exploration, you're of course hurting yourself because you delay your learning, you learn later. Your learning takes longer, but you're not acting too crazy in terms of performance, and you can remain in the system until you reach your eventual performance. So this is a very is an application of this problem. The other application that you can think of again of this problem is going back to, this is a little bit maybe more involved to explain, but you can think about it in a kind of like a Bayesian way. And what is the Bayesian way? So whenever you go to get an advice, so from your doctor, from your teacher, from your professor, right? So you're not coming out of a vacuum. You have already a prior about what is the right answer should be, right? So now if you go to your advisor, an advisor takes an exploratory action on you, which means that there is a big difference between the performance of that and your belief. Then the first time you say, okay, but the second time, third time, then you say, okay, this advisor or this doctor is no good because everything says I have to take an aspirin, but this doctor is giving me something that is very different than aspirin because he's taking his exploratory action, right? So if this exploration is too much, you're going to lose customers. So you have to control this exploration to a certain level. If you ask your professor 10 times for advice and 2 of them are bad, 8 of them are good, you still go back to that supervisor. But if, I don't know, 8 is bad and 2 is good, then you're going to abandon that website and you're not going to go for recommendation there. So this is exactly the same thing. You're controlling your exploration. Actually, there is a very nice paper by Alex Slifkin and Yisham Mansour that they are looking at the problem in this kind of a Bayesian way, that their baseline is the belief of the user or the learner. And the deviation or the constraint is how much this belief is different than the actual recommendation of the system. And the situation is exactly the same. With too explorative, you're going to run away. Right? So this is for that. For the second problem, the most important application for me is the multi-objective problems, because there are a lot of problems that there is a metric that is the main metric that you are trying to optimize, and there are a bunch of metrics that you need to make sure that you're not screwing it up. For example, in recommendation, we all know that if I show you something that is very, very offensive or aggressive, you're going to definitely watch it, but you may not come back to me, right? So the watch is high, but the return is also low, right? I show you something very offensive. You're going to watch it, say, who's this crazy guy showing me this? But you're not going to come back to me because I'm showing you something very offensive, right? So these are 2 objectives that I'm optimizing, right? If companies are not careful about this, whenever you go and watch something or on the internet, they show you the most disgusting thing possible because it has the maximum click. So here is exactly the same formulation, that there are multiple metrics that should be controlled and one metric should be optimized.
Thank you very much.
All right. Any other question? So I have a question. So obviously in the upper confidence bound, we need to use the upper bound, right? But it reminds me of robust optimization, right? In robust optimization, you would try to maximize the minimum performance over some neighborhood of your point. Is there some relation to robust optimization, or is that just a coincidence?
Okay, so let me first clarify a little bit. So upper confidence bound formulation in exploration is something that is independent of constraint. So if you look at all Bandit algorithms, they are all based on this optimistic view that you calculate a confidence set that contains your quantity of interest, which in this case is the mean of the distribution. But then you look at the maximum value of this quantity in that interval, and then you judge different actions according to their optimistic value. Right? So you say the mean of this arm is maximum this, the mean of this arm that maximum this. I take the one that has the maximum of maximum. So this is the optimistic view, and this is independent of the robust optimization. But when you go to constraint, then what you're saying is exactly right. So now you have this confidence set. You look at your performance as the worst possible scenario in this interval. So you look at the lower bound of that interval. And then your adversary or the other part of the constraint, you look at this best case formulation. And this is exactly the min-max, standard min-max of robust optimization. Then you look at your worst case versus the best case of the opponent. And if your worst case is still better than the base case, or your worst case still satisfies the constraint, then you're confident that you're going to be good if you take that action. And if you can see, when I was comparing myself versus the baseline, I said, if I know the baseline, I compare my worst case with the baseline. If I don't know the performance of the baseline, I look at my worst case versus the best case of the baseline. And this is exactly the min-max in the robust optimization that you mentioned. And if I still satisfy these, then this action satisfies the constraint. So it goes to the feasible actions. So exactly, in the constraint case, we have the min-max of the robust optimization. Sometimes, since the baseline is known, it's not really a min-max, it's mean versus the baseline. But if the baseline is not known, it becomes exactly the min-max formulation. But that's, I would like you to discriminate that with the whole idea of upper confidence bound. Upper confidence bound and this optimistic view in exploration is independent of constraint, and it's doesn't have any connection to robust optimization. But the min-max, yes.
All right, thanks. That clears up things. Any other questions here? The audience? No, then let's thank Mohammad again.
Thank you very much. And if there is any other question, the papers are on the slides. And if you have any question, just feel free to drop me a line, and I would be happy to answer the questions offline.
All right, great. Thank you very much.
Thank you.